Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we will extend the application of MAC algorithm for solving energy equation. And before we start the solution part, we'll just briefly mention about higher order upwind differencing. And we have shown a grid template which already you know. Basically the velocity quantities are defined at the center of the cell faces to which they are normal, like you can see Uij, Vij, and the pressure and temperature are defined at the center of the cells. Having said that, if we want to discretize a convective term like del x of u phi, phi is a scalar quantity and phi ij is the location of phi at a cell identified by ij. So del x of u phi, we have written in conservative form, will be u phi I plus half j minus u phi I minus half j by delta x. And this phi I plus half j and phi I minus half j can be defined by the expressions 24 and 25. Separate expressions are written for upwinding, and you can see if local velocity is negative, then it will have the expression which is given by 24, and the local velocity is positive, then the expression is given by 25, because depending on the direction of the velocity, we have to engage the upstream points. And this quantity xi is basically a parameter involved with upwinding strategy, and value of this parameter, for example, if we go by quick scheme, as you know, quick is a very popular scheme, and the value of xi in quick scheme is 3 by 8. Quick stands for quadratic upstream interpolation of convective kinematics. It was developed by Professor Leonard in 1979. I mean, I have given just an example. One can use quick scheme, one can use several other schemes. Again, I have given two more examples, like Kohara scheme, which was developed in 1986, and INO scheme. INO scheme, basically INO stands for essentially non-oscillatory scheme of Professor Stanley Osher. This is a very, very accurate scheme, INO scheme, used for even modeling free surface flows. Now we will come to energy equation. You can see we have written energy equation as a general expression. Rho Cp total derivative of t, that is dt, d time, and this has the temporal derivative and the spatial derivatives equal to k grad square t plus u phi star. Now we have done a little sort of change here. Change means no major change in nomenclature. That is, start quantities we are considering as non-dimensional start quantities. Again, sorry for this mistake. Start quantities are dimensional quantities. Usually start quantities are non-dimensional quantities. We have taken start quantities as dimensional quantities so that after non-dimensionalization we get usual terms as non-dimensional terms. So you can see that U starred, V starred, W starred, or X starred, Y starred, Z starred, all these starred terms are here we are using for dimensional quantities. Similarly, T star is dimensional time and uppercase T is dimensional temperature. And then we non-dimensionalize in this way that small u is u star by u infinity, small v is v star by u infinity, w is w star by u infinity, theta is t minus t infinity divided by tw minus t infinity, and x is x star by L. So L is the reference dimension of the domain, u infinity is the reference velocity, T infinity is the lowest temperature available in the field, and Tw is the highest temperature available in the field, so that non-dimensional temperature varies between 0 and 1. And non-dimensional time is T star divided by L by U infinity. So if we define the non-dimensional variables in this way, then we can plug in these variables into the dimensional equation given by equation 26, and we can get this non-dimensional form of equation given by del theta del t plus u del theta del x plus v del theta del y plus w del theta del z equal to 1 by Peclet number. Peclet number means Reynolds number into Prandtl number. Del 2 theta del x2 del 2 theta del y2 del 2 theta del z2 plus Eckert number by Reynolds number into phi. Phi is again non-dimensional dissipation function. So we can then look at whether this viscous dissipation we will retain or not. So if Eckert number is given by velocity, reference velocity squared divided by Cp Tw minus T infinity, then 1 by Eckert number we can write this way. From here we can see that Cp T infinity by U infinity square, again we can write in this way, Cp nu r T infinity divided by nu r U infinity square. Sorry, Cp gamma r. I'm again done a mistake. So Cp gamma r T infinity divided by gamma r U infinity square. Gamma r is introduced because gamma is basically ratio of specific heats, Cp by Cv, and r is the gas constant given by is basically Cp minus Cv. So r is Cp minus Cv and gamma is Cp by Cv, and local acoustic velocity is given by uppercase C, which is root over gamma r T infinity. and we also define Mach number, which is velocity divided by local acoustic velocity. So this Cp T infinity by U infinity square, with little bit of algebraic manipulation, we can write it as, you can see, 1 by gamma minus 1 multiplied by 1 by Mach number square. So 1 by Eckart number, then this is the expression, this was the expression for 1 by Eckart number. So 1 by Eckart number becomes 1 by gamma minus 1 into Mach number square into Tw by T infinity minus 1. That means Eckart number becomes gamma minus 1 into Mach number square divided by temperature ratio, highest temperature and lowest temperature ratio in the flow field. Our reference temperature is T infinity. Tw, if there is any heated objects, temperature of that heated object or heated wall. If it is flowing internal flow, maybe wall is heated to a temperature Tw. So Tw by T infinity is the temperature ratio available in the flow field. We can say highest by lowest temperature ratio minus 1. So Eckart number is given by this. Now we can go for little order of magnitude analysis. Usually gamma for diatomic gases or gamma for air can be taken as 1.3 or 1.4, and then this becomes a decimal quantity, gamma minus 1. Mach number for incompressible flows, it is less than 0.3. Even if we take 0.3, so it is 0.3 square. It's a small number. And finally, divided by temperature ratio, which may be 1.8, 1.7, 1. Whatever, minus 1. This is also a small quantity, or temperature ratio, if it is maybe 2, then it will be 1. So whatever is the denominator, we can see that numerator is basically if Mach number is 0.3 and if we say gamma is 1.3, so it is 0.3 cube. So it's a very small number after, this is starts from the decimal point, and this multiplier may be so small, and then further it will be divided by Reynolds number, and usually Reynolds number is moderate to large for such cases. So Eckart number by Reynolds number is a very small quantity. If phi is not too large, that means viscous dissipation function, then this Eckart number by Reynolds number can be ignored. As I said, estimation is this is 0.3 cube Eckart number, and from gamma minus 1 into Mach number square, and divided by Reynolds number. So it is a very, very small number with respect to the contribution of other terms, and we can neglect that. If we neglect that, we can retain also, then it will be added as a source term, but for the time being we are neglecting it, and we are sort of redefining the equation as del del x of u theta, del del y of v theta, del del z of w theta, convective terms, equal to 1 by Peclet number del 2 theta, del x2, del 2 theta, del y2, del 2 theta, del c2. Here one can also mentioned that usually this contribution of, I have said that it is basically it will behave as source term, because when we are coming to solve this equation, we have already solved the velocity field. So even though this multiplier Rickard number by Reynolds number square into viscous dissipation function, they will be having u, v and w, but since u, v, w are known a priori, so they can be those can be evaluated, and that will be added as a source term. And here we are ignoring it. And also you can see that since u, v and w are already known, and we will be plugging in those terms from the solution of momentum equation, the nonlinearity of energy equation is also not there. So now we can write this equation as del square theta equal to Peclet number into convective terms. And we are solving, you can see the unsteady term is dropped, the steady state energy equation, because for a given velocity field, energy equation will finally converge to a steady state temperature field. Velocity field may vary, so for varying velocity, for any given velocity field, we can get a steady temperature field. So now so this convective our solution strategy will be something like pseudo time marching. Here this m index superscript, this does not signify time level but iteration level, and so convective terms at ijk point at mth iteration level. And del square theta we can simply discretize as the central difference in x direction, central difference in y direction, central difference in z direction. And we can again consider Peclet number into this convective terms contribution. This is known, and we can call this as S star m. Just we have used this nomenclature. We will call Peclet number into the contribution of convective terms at mth level, mth iteration level, as S star m. And left hand side del square theta we have discretized following central difference scheme in x direction, y direction and z direction. Now as I said, S star m is basically, we have defined this is Peclet number into the contribution of the convective terms at the mth level at a point ijk. So we have written that del x of u theta, del y of v theta, del z of w theta is basically contribution of convective terms at a point ijk at a level, it's not time level, there's iterative level m. And then we have given the expressions for del x of u theta, del y of v theta, del z of w theta. And we have followed the same second upwind method for discretization. For the convective terms, we have followed the second upwind method of discretization, and if we recall, basically we have the terms del x of u theta, del y of v theta, and del z of w theta. Now we have taken up the first term, which is del x of u theta. Now del x of u theta, we have to discretize where theta I j k has been defined. That means basically we have to define theta at this point together with uijk, because this is here we are using conservative form, so u and theta are to be defined here. U is defined here as uijk, and theta here will be theta ijk plus theta I plus 1 jk by 2. So we have written that uijk into theta ijk plus theta I plus 1 jk by 2. So u and theta both have been defined here, minus u and theta here. So here u is u I minus 1 jk, and theta is theta I minus 1 jk plus theta I jk by 2. So u I minus 1 jk multiplied by theta I minus 1 jk plus theta I jk by 2. So u I minus 1 jk here, and theta I minus 1 jk plus theta I jk by 2, that is theta here, we have defined, and difference between these two divided by delta x, sort of central difference. Why exactly central difference? We have done that, and then we have introduced the upwinding factor, and also together with giving upwind bias, we have introduced modular sign, so that the formulation can take care of positive and negative both uijk at this point. And similarly also we have introduced this modular sign over ui minus 1 jk. So ui minus 1 jk, it can be positive locally, it is possible somewhere it can be positive, somewhere it can be negative. So we, in order to take care of that variation of velocity, we have introduced modular sign here, and here this ijk uijk, this also can be locally positive or negative. For introducing that flexibility, we have used the modular sign here, and this is basically, these are the upwind contributions, and upwind contribution is identified together with alpha. Alpha is the upwind factor, and if we recall what we did for the momentum equations, recommendation was alpha may be varied between 0.2 and 0.3. It may be even less. Lesser is always better, but it should not cross 0.3, because less alpha means it is inclined more towards central differencing, second order accuracy, and alpha is giving the upwind contribution, but it should be kept at a minimum level, at a low value of alpha should be used. So this is how we have discretized del x of u theta following second upwind method, which we also followed for the momentum equations. And same way we can discretize del y of v theta and del z of w theta, and then we'll have contributions of all the individual terms of the convective part of the energy equation. So this is how I have given the example del x of u theta, similarly del x of v theta, del y of v theta, del z of w theta. Those are to be discretized, and this is these are the expression for discretized del x of u theta, del y of v theta, and del z of w theta terms. Once we know all this, we know what is basically discretized convective terms at point ijk at a level m, and if we multiply it with Peclet number, we will get S star m. Now, S star m equal to this, and this is known. Now, let us go back again, don't confuse, go back to equation 30. So this term we have evaluated. Left hand side we had basically central difference, we use central difference scheme to discretize del square theta in x, y and z direction, and we can see that it involves theta ijk and its neighbors I plus 1 jk, I minus 1 jk, ij plus 1k, ij minus 1k, ijk plus 1, ijk minus 1. So theta ijk and the neighboring thetas are involved on the left hand side. Now again let us go back to the expression. We know now the quantity is star m, and left hand side we had central differencing of theta in x, y and z direction. Now in that expression for central difference, discretized theta, we are pulling out theta ijk terms. So theta ijk, twice theta ijk by delta x square, twice theta ijk by delta y square, twice theta ijk by delta z square with negative sign, and all the neighboring terms, that means theta I plus 1 jk plus theta I minus 1 jk by delta x square, theta I j plus 1k plus theta I j minus 1k by delta x square. So all those neighboring terms, we are calling them as A star m. We are deliberately doing that. We will assume that at a given level, theta is known. Theta can be, when we are starting the computation, theta are initial temperatures are all thetas. So if it is known for the when we are going for the next level, if the previous level is known, we can call them together is star to the power star m, and we can then from this expression we can get a clearly explicit expression for theta ijk. So theta ijk then will be A star m minus S S star m divided by twice delta x 2 by delta x square plus 2 by delta y square plus 2 by delta z square. Whereas as I told, A star am is at the mth level neighboring terms of theta ijk, like theta I plus 1 jk plus theta I minus 1 jk at the level m by delta x square, theta ij plus 1k plus theta ij minus 1k at the level m by delta y square, theta ijk plus 1 plus theta ijk minus 1 at the level m by delta z square. So theta ijk, when at mth level, this A star, which is comprising of Peclet number in two convective terms at mth level, these are known. Neighboring theta values, neighboring cell theta values at the neighboring cell at mth level, those are known, divided by this 2 by delta x square, 2 by delta y square, 2 by delta z square. We can get new theta ij distribution on all cells if we run from I equal to 1 to IIM, j equal to 1 to JIM, and k equal to 1 to KIM. But here, point by point, we'll be able to get that. So if that is improved or new theta ijk, we can call it m prime. So theta ijk m prime, let us assume we are calculating through equation 31. Then in equation 32, theta ijk m prime minus theta ijk m, this quantity multiplied by omega. Omega is again an over relaxation factor, plus theta ijk m. This is theta ijk, we can call it m plus 1. So we are accelerating this calculation by introducing a over relaxation factor, which is maybe 1.3, 1.4, 1.5. We have to do a little bit of numerical a priori study to find out a proper omega for a good level of acceleration. So we have written in order to describe equation 32 that theta ijk m is the previous value, theta ijk m prime is the most recent value calculated from equation 31, and theta ijk m plus 1 the calculated better guess. So it is even more improved guess when we are trying to converge going for the steady state temperature. The procedure will continue till the required convergence is achieved. This is equivalent to Gauss-Seidel procedure for solving a system of linear equations. So that is how, just following this Gauss-Seidel procedure, Gauss-Seidel procedure for solving linear equations, we can solve then theta and can repeat the iterative loop till the steady state temperature is reached. So this is the overall strategy for solving the energy equation and finding out temperature at each cell. But we must remember that in this case, specifically what we have discussed, we have solved the Navier-Stokes equations, that means momentum equations in advance, and found out the velocity quantities u, v and w at each cell. Then we are solving the energy equation. So now I will give one or two very successful computations. There are many, but I am giving just one or two examples because these are very complex flow fields. First example I am giving, that flow pass stay delta winglet in a channel. See, this is the delta winglet, and approach flow coming from, you can well understand, from the other side. Obviously, the side of the winglet which we cannot see, that is facing the flow, and there will be higher pressure on that side, and downstream side will have lower pressure, and because of creation of this pressure surface and suction surface, aerodynamically this side is called suction surface, the vortices will be created. So this is, if we call main vortex, we'll get, and this is a longitudinal vortex, we'll get another such longitudinal vortex which will be created on the opposite side, which we cannot see, which will be created on that side due to the difference of stagnation pressure from the top of the wing to the bottom of the wing. Because you can see the velocity head will be converted into pressure head, and obviously velocity is having a gradient, and that is why this stagnation pressure will also have a gradient, and depending on the velocity, like on the top side it will be having higher pressure, and the bottom side it will be having lower pressure. Due to that, another vortex will be created, which is called corner vortex. The creation of this vortex follows the basic philosophy of horseshoe vortex. So this will be another vortex, and the fluid between these two vortices will also undergo a rotation. So it will be a very complex field of this combined vortices. If we go in the downstream on any plane, we have to get footprint of all these three vortices. That means main vortex, horseshoe vortex or corner vortex, and fluid in between will be induced, will create induced vortex. So now this is the you can see computational result, and we can see main vortex, corner vortex, induced vortex. I mean, because after these vortices are created, they will be disseminated, they will be in the downstream, and they will spread also. And you can see here this induced vortex, main corner vortex, main vortex, induced vortex, and these are all experimentally determined field, and hot wire anemometer was used, and on a cross plane about 2000 points were taken to determine u, v and w velocity on 2000 points using hot wire anemometer. And this is the after data reduction, it was through a DDA card, it was fed to a computer, and a computer calculation was done in vorticity field in the post-processing program, and this was plotted. And this is computational vorticity field, where we also can see corner vortex, induced vortex, main vortex, etc. And the closer comparison even gives better satisfaction. So vorticity contours behind a cross plane xc equal to 2.5. This is the distance behind the winglet. Winglet is placed at beta equal to this angle, beta angle at 150 degree, and A are experimental results, B are computational results. Why I showed this is a very complex field, because here whatever I have shown schematically, this scheme doesn't stay static there, because these vortices keep interacting and they spread all over the domain, all over the cross plane, and depending on distance from the winglet trailing edge, this structure keeps changing, and we have shown the flow structure at x equal to 2.5. And as I have said, that we got amazing match with the experimentally determined flow field. Then we will take up yet another example. Here, instead of delta winglet, we have used delta winglet pair. And this is a very well-known experiment. This experiment was done in Stanford University. Professor Pauli and Professor Eaton were involved. This was basically Professor John Eaton's experimental group. And this is a channel. You can see channel dimensions, and these are relatively smaller dimensions, and delta winglet pair is sitting here, and again behind the winglet the flow field at different cross sections, flow fields were mapped experimentally by Professor Eaton and Professor Pauli, and we calculated the velocity fields at the same axial location. We calculated entire velocity field and then plotted at the same axial locations where the results of Professor Eaton and Professor Pauli were available. So you can see at a distance x equal to 97 centimeter behind the winglet pair, at a distance 142 centimeter behind the winglet pair, at a distance 188 centimeter behind the winglet pair, and at the same we computed the entire field, and at the same location cross planes we plotted the velocity vectors. You can see excellent match. But since this is turbulent flow, I will not say this is excellent match, because such quantities in matching such quantities in turbulent flow is possible, but that is not the complete confirmation when it is turbulent flow. There are quantities like second moment, which are root mean square velocities, or skewness factor, flatness factor. These are third moment and higher order moments. These are to be evaluated critically, but from the engineering point of view, from the matching of velocity vectors, this produced a reliable result. So I will just give you some references which are very useful references with respect to the MAC algorithm and its application for solving flow and temperature fields. Whatever references I used in my lecture, I have discussed or given those references. If you like, you can look at these papers and gather more knowledge and enhance your understanding. Thank you very much for listening to the lecture with attention. Thank you.